All right, so today we are diving into what is basically a mathematical ghost story. It's a wild tale about a brilliant idea, an idea that powered one of the greatest inventions in history, only to be banished for being, well, logically unsound. But then, centuries later, it was proven right all along.
So it all kicks off with a really simple, kind of intuitive question. If you take any curve and you just zoom in, and I mean really zoom in, doesn't it start to look straight? So what if a curve is secretly just made up of a bazillion of these tiny, tiny straight pieces? This is the core idea that literally gave birth to calculus, but it relied on something a little bit problematic.
And here it is. Meet the infinitesimal. This is our ghost in the mathematical machine. I want you to imagine a number that's so ridiculously small you can't even name it, you can't measure it, but here's the catch. It's not zero. The folks who invented calculus used this idea to do absolutely amazing things, but it drove the logicians completely nuts. I mean, how can something exist if you can't even properly define it? This powerful ghost was about to get exorcised.
Okay, so let's set the stage for this whole controversy which lasted for centuries. How in the world did such a useful idea become public enemy number one in the world of math?
You know, back when calculus was first being cooked up, infinitesimals were the perfect tool. They let mathematicians slice up curves, figure out complex areas, even predict the motion of the planets. And here's the crazy part. The answers they got were right. The method was unbelievably powerful. There was just one teeny tiny problem. Nobody could really explain why it worked.
So the math community basically had to make a choice. And they did. They decided to rebuild the entire foundation of calculus from the ground up, using a concept that was way more rigorous, but honestly, a lot less intuitive. It's called the limit. And with that, infinitesimals, these incredibly useful ghosts of departed quantities, were officially kicked out of polite mathematical society. They were seen as a useful trick, a fiction, but a fiction nonetheless. But, you know, not everyone was ready to let go. And this brings us to the first hero of our story, a 19th century physicist who saw the power in that ghost and absolutely refused to give it up.
So this is Siméon-Denis Poisson. Now, he was a pragmatist, a get-it-done kind of guy. While all the pure mathematicians were off in a corner debating logical purity, Poisson was busy, describing the entire universe. For him, if using infinitesimals gave the right answers in physics, well, that was good enough. He didn't banish them. No, he wrote a playbook for how to use them safely.
And Poisson's playbook was just filled with common sense. It basically said, first, look, let's just agree these little infinitesimal things are real. Okay? Good. Second, if a difference is infinitesimally small, we can probably just ignore it. Third, an integral, that scary thing from calculus, it's really just simple addition. You're just adding up an infinite number of tiny slices. And finally, and this is the big one, if you zoom in enough, any curve just becomes a straight line. These were his working rules.
Now, Poisson's rules worked, but they were still just intuitive. They were just rules of thumb. The why was still missing. And for that piece of the puzzle, we have to jump way forward, into the 21st century, and learn a totally new language for talking about infinity itself.
Okay, so this new language is called the theory of infinity, or TOI for short, and it starts by completely flipping our idea of infinity on its head. So instead of thinking of infinity as some endpoint you count up to forever, TOI says infinity is the raw material, the creative chaos from which everything else, including numbers, is carved out.
So if infinity is just chaos, how do we get any order out of it? Well, that's where the second big idea comes in, symmetry. Think of symmetry as this universal organizing force. It's the set of rules that takes all that infinite potential and carves out stable, predictable structures, kind of like a crystal forming in a liquid, or a perfect snowflake forming out of water vapor.
The third idea is closure, and this one is absolutely crucial. Closure is the principle that lets an infinite process actually produce a finite result. So imagine a machine, and you're feeding it this never-ending stream of tiny inputs, like adding fractions that get smaller and smaller and smaller forever. Closure is the part of the machine that just seals that whole infinite process off and spits out one single stable answer.
And finally, we have context refinement. The best way to think about this is like having an infinite zoom lens. It means you can always look closer at a problem. And when you do, you reveal a new, more detailed context. And you can do this forever. There's no bottom floor. And this is the principle that logically allows for infinitesimals to exist. They just live in these infinitely more zoomed-in contexts. So now we have Poisson's old-school intuitive rules on one hand and TOI's new, rigorous language on the other. And now, for the magic trick, we're going to translate the old intuition into the new logic. This is the moment where the ghost is finally explained.
Let's see exactly how this works. Remember Poisson's rule that a tiny piece of a curve is basically a straight line? Well, in the language of toy, that's not just a cute trick, it's a fundamental principle. At that infinitesimal scale, the force of local symmetry makes the straight tangent line the most dominant feature. And then, the principle of closure comes in and locks in that simple straight line view as the correct description for that specific scale. Poisson's intuition was a perfect match for these deep structural forces.
And what about his idea that an integral is just an infinite sum of tiny pieces? It's the exact same story. The TOI principle of context refinement is what gives you that infinite supply of tiny slices to add up. And what is the adding? Closure. It takes that infinite, messy sum, seals it all up, and gives you the single, finite number that is the answer to the integral. The language of TOI perfectly describes the process Poisson was using all along.
So here's the absolute heart of the matter. Poisson wasn't cheating. His practical rules weren't just lucky shortcuts that happened to work. No, they were a stunningly accurate, intuitive grasp of a deep mathematical structure that it would take science another 150 years to develop the language to even describe.
So this brings us to the big picture. What does this story of a mathematical ghost and its ultimate redemption really tell us about, well, everything?
I mean, this isn't just a quirky little piece of math history. It's a really profound lesson in how knowledge itself works. Sometimes, an old idea isn't wrong, it's just waiting. It's waiting for a new perspective, a new tool, or a whole new language to come along that can finally show everyone the deep truth it held inside all along.
And that brings us to the ultimate takeaway, which I think is captured perfectly by this idea. New theories don't just create the future, they can also redeem the past. We tend to think of progress as this one-way street, right? We leave old ideas in the dust. But sometimes the most powerful thing a new theory can do is look backward and finally give a voice to a ghost.
It really makes you wonder, doesn't it? What other intuitive but unproven ideas are out there right now? In physics, in biology, maybe even in philosophy? What other scientific ghosts are just floating around, waiting for us to invent the right words so we can finally understand what they've been trying to tell us this whole time?